So yesterday I spoke to the German Chemical Society about the work that I am doing that relates to solving the world's energy problems. In fact, the title of the talk was How Quantum Mechanics Can Help Solve the World's Energy Problems. Someone said to me that it was a very bold title, but I think that anyone who has the expertise to contribute to helping solve the world's energy problems should be doing so, because it is a daunting task in terms of there is no one solution in the energy arena that's going to be the magic bullet that will solve all of our problems for centuries onward. And so there's plenty of room both to do really beautiful basic science, but also to have a real impact on the world. So what I talked about was the work that we're doing that starts with the basic fundamental laws of physics, the quantum mechanics, that describes the distribution of electrons both in space and in energy, in materials and molecules, and how that fundamental equation that governs the behavior of electrons in molecules and materials, namely the Schrödinger equation, can be approximated now in a way that is efficient and yet doesn't lose accuracy for many properties of interest, so that you can study a wide variety of problems that relate, in my case, to energy, from work I've done over many years in understanding and working to help optimize protective coatings for jet turbine engines, and that, based on quantum mechanics, understanding what is it that leads to a good coating versus making the coating. These are ceramic coatings that protect a jet engine from the very, very high temperatures. The engine components are made of metals that the temperature of the engine is actually, the operating temperature is above the melting point of the metal alloy from which the engine is comprised. But by putting a ceramic coating along with cooling air, one can actually fly in airplanes and generate electricity using these turbine engines. And that's in fact the basis of our air transport and much of our electricity generation. That's one area that I've worked in. Another area that I'm working in currently is to use quantum mechanics to understand the thermochemistry and kinetics associated with the burning of biofuels, new advanced fuels that are coming out from, for example, the lipids that are produced by algae. Another area that I am working in is to use the techniques that we've developed, the quantum mechanical techniques, to study mechanical properties of lightweight alloys that could be used, for example, in vehicles to lighten their weight so that we would have improved fuel efficiency. These are some of the areas that I worked in. The areas that I focused on yesterday actually have to do more with solar energy, and as well as fuel cells. And so we've done a lot of work related to thinking about how you can go beyond the traditional semiconductors that have been used most of the time for example, converting sunlight to electricity in photovoltaics. But going one step further and thinking about photocatalysis, how you take the exact same phenomenon that goes on in photovoltaics, but take it one step further to do chemistry that can convert carbon dioxide, water, the combustion products, and turn the reaction around to reduce them to produce, using the energy from sunlight, to produce fuels, for example, methanol. And methanol itself, of course, is not a very good fuel, but we know with zeolite catalysts that it can be turned into gasoline. So there are lots of opportunities in this area, and our contribution has been to explore the use of transition metal oxides as both light absorbers, transmittance of charge carriers, not an easy thing, definitely a complicated situation because of their they tend to be less mobile than in traditional semiconductors. So there's lots of things that have to be done to optimize them. But transition metal oxides are traditionally used as catalysts, and so they are very promising in terms of combining their catalytic properties along with sunlight absorption and following the whole phenomenon through, from absorption through generation of charge carriers onto redox chemistry. So these are the things that we've been doing, is looking at how you can alloy or dope transition metal oxides to get optimal properties. So that's about what I talked about.